Okay, today we're talking about magnets. We are going to look just a little bit about some similarities and some differences between magnetic things and electric things. Now, I'm going to try not to get into too much detail about the electric piece of information throughout this lesson because that's actually what we're going to be discussing in detail for the remainder of this chapter and for all of the next chapter. But one thing that it says here that is different, an important difference between magnets and electric charges, is that electric charges can be isolated and magnets cannot. What we mean by that is we can have an object or even an individual atom that is only solely negatively charged. And then completely separately, we could have an object or an individual atom that is positively charged. So sometimes we have both positives and negatives present, which would then make our object neutral, but we could have a positively charged thing or we could have a negatively charged thing. With magnets, it doesn't work that way. Instead of having positive and negative charges, what we have are north and south poles. You cannot have just a north pole all by itself. And what they are trying to show us in this illustration over here to the right is that my magnet will always have a north pole and a south pole. Even if I were to take this magnet and break it in half, I'm going to have a north and a south end on that smaller piece. If I were to take this magnet and break it yet again, each of those pieces would also still have a north end and a south end. So this is what we mean when we say that magnetic poles cannot be isolated. You will always have both north and south poles together, no matter how small our magnet. Now, what creates magnetic properties, what makes an object a magnet, depends on what we call magnetic domains. So what we're looking at here is an illustration of, this illustration is trying to show the movement of electrons. So we should have learned way back in middle school, we talked about it again in chemistry, we talked about it a little bit earlier in our physics class, that electrons are located outside of the nucleus of the atom and they are constantly in motion. When we look at this illustration, they are trying to give us these arrows to give us an indication of the movement pattern of those electrons. So when we look at this unmagnetized iron, we call it an unmagnetized iron because right now this piece of iron is not magnetic. If we look at these arrows, they are unorganized. They're all pointing in different directions. Each of these electrons are moving, but they're all moving in their own little path. They're not in unison. What makes something magnetic is when the electrons for the atoms of that particular object or that material are all moving together in unison. So when we look here at this strongly magnetized iron, what we see now is that all of the arrows are pointing in the same direction, indicating that the electrons for all of those atoms are moving along the same route now. Now they're all in the same path, or they're moving what we like to say in the same direction. And that is what makes our materials magnetic. So we call this a magnetic domain. And this is when the movement of those electrons are all along the same direction, or what it says over here is that these atoms are aligned. The electrons of these atoms are aligned. They're all moving together in unison, and that is what makes our materials magnetic. All right, once again, let's review that we will always have a north pole and a south pole. You can never have just one of them. So what we need to understand, not only that we will always have a north and a south, but when we take two magnets and we put them together, they will interact depending on whether or not we have paired up the north ends or the south ends or one of each of those two magnets. So what we're looking at this picture here on the bottom is two magnets that have been placed near each other. And what we see here in the middle is that we have a north pole and we have a south pole. And because these are opposites, they are going to be attracted to each other. So what we're going to see if we were to physically hold these two magnets close to each other is that they would move together and meet up in the middle, and then they would be joined together. So when we say opposites attract, that's what we mean. We mean that they are going to be drawn closer together, or they are going to move closer because they are drawn together. They are attracted to each other. If we were to turn this magnet around and instead have two north ends facing each other, so if I were to, or let's make it two south ends, sure, out of convenience for my drawing. So if this magnet had the south side here and the north side here, so let's just make this so that it matches our picture real quick. So if this is the north end and that is the south end, now these two magnets are not going to want to join together. These are what we call like poles, meaning that they are of the same kind. So in this case, it is a south and a south that I have brought close to each other. And because they are the same, they are going to repel. So this word repel means that they are going to push apart or push away from each other. So these two are going to want to move away from each other. So this south magnet and that south magnet are going to physically push away, and there will be more space between those two magnets. If I were to try to bring them together, if I'm physically holding them in my hand, there would be some actual physical resistance, a force that I could feel trying to push my hands apart as I try to make those two south ends come together. So we say opposites attract, so a north and a south will be drawn together, like repel. So if whether it's a south and a south or a north and a north, they are going to want to separate and they're going to push away from each other. What we're looking at here is something called a magnetic field. So if you've ever seen a video or an illustration of a magnet where they take those iron filings and they just sprinkle them around the magnet, you can just dump them out on top of the glass or the paper, the screen, whatever it is that they've got separating the magnet from those iron filings. And at first, they just get dumped on the paper, but then very quickly you see that they kind of start to move and arrange themselves until they make this cool little image of all of these lines or stripes coming out of the magnet. Well, those are called magnetic field lines. And so in each of these illustrations, they have provided some magnetic field lines for us. So let's just talk about what you are responsible for knowing about magnetic field or the magnetic field lines specifically. So we are going to have an actual direction. If you look closely, this is an arrow coming out of the north side of this magnet. If we focus on this half of the line, we are going to see this as an arrow pointing into the south side of the magnet. So what we say is that the magnetic field lines go out of the north end and into the south end of our magnet. So when we draw it together, we see this full arch where we are coming out of the north end of the magnet and into the south end. And because opposites attract, we end up with this image that shows a complete connection between the north and the south end of our magnet. If we look at this illustration down here below it, this is not a U-shaped magnet. This is a regular bar magnet. So we have arrows coming out of the north end. We have arrows going into the south end, right? But if we were to throw those iron filings on top of a piece of glass with a magnet underneath it, what we would see is there is actually a connection within one single magnet connecting the north to the south because opposites attract, okay? So when we ask you, make sure you know the direction, that's what we like to call it, is out of the north and into the south. Now, this is just a little bit of a fun fact, but you are going to be responsible for knowing this fun fact. It's talking here about the magnetic poles of the earth. when you learn about the Earth and you learn about the location of the different places, the different landmarks on the Earth, you also learn about the North Pole and the South Pole. So on our map, if we are looking at just a map of the Earth or looking at a globe, we say that the North Pole is here at the top of our globe, and we say that the South Pole is down here. Well, when we're talking about magnetic fields, because we should have learned in earth science that we've got this super hot core inside the middle of the earth, and so that is actually a liquid, and we've got lots of movement going on because of that superheated liquid, that magma inside of the earth's core. Well, that actually creates a magnetic field inside of the earth. So the earth has an actual magnetic north pole and a magnetic south pole. So what it is saying here is that the magnetic poles that we learn on a map are actually not the same as the actual magnetic north and magnetic south. So what we call, the geographic poles, north and south, what I have illustrated here on the map, those are not the same location as the actual North Pole and South Pole when we're talking magnetic fields. The reason for that is because that superheated core is moving, and so it just causes shifts in the placement of the location of the magnetic north and the magnetic south end of the Earth's core, and that's what it's saying down here. It's just constantly moving. So it's really hard to say this is where it's located because the location of the north magnetic field at this moment will not be the same that it will be at a later time because it's constantly moving. So just a fun fact that I want you to know, okay? Magnetic poles are not the actual same physical location as the geographic north and south poles that we have learned. All right, so now let's talk about a little bit about why we have magnets in the same chapter that we're talking about electric charges. And the reason is because they are directly connected. If you think back to our electromagnetic waves that we learned, did you ever wonder why we called it electromagnetic? Like, did it sound like two words were just smushed together? Because it should have. And the reason for that is because it is. We have a relationship here between magnetic fields and electrical charges. And so what we're going to talk about right now is just a little bit of that relationship as it pertains to understanding magnets and what we call electromagnets. Then in the upcoming lessons, we'll talk in more detail about the electric charges and understand those and the movement of those a little bit better. But basically, what we're looking at here is an illustration of an electromagnetic wave. Now, in a previous lesson, I gave you an image of a light wave, and it looked really similar to this because a light wave is an electromagnetic wave. And at the time, we didn't really stop and look in detail about the two different parts to the wave, but if you notice here, I've got a purple and I've got a pink part, and they have different labels to them. One is focusing on the magnetic field and the other is focusing on the electric field. So our electromagnetic waves, including light, has both electric and magnetic properties to it. So because we naturally have this relationship between the two, then we can often talk about electric currents and magnets in conjunction with each other, okay? So what we're going to talk about now is we're actually going to ignore this slide for the time being because that is part of the details that we'll get in a later lesson. But it's saying here that the magnetic fields of our materials comes from those moving electrons, as I stated earlier when we talked about those magnetic domains. So when our electrons are moving, they actually also create a magnetic field. So the magnetic field comes from the moving electrons, okay? And so that's really the gist of what I need you to know right now. So when I quiz you over what kind of field does our electron have, your options are going to be electric fields and magnetic fields. Now, if we're talking about electrons, electrons are always going to have an electric field. So this is talking about electron, and yep, we have an electric field. This is talking about electron, and sure enough, we have an electric field. The difference between these two little lists is the word in front of the electron. If we have a stationary electron, stationary means not moving. If we have a stationary electron, that means it is only going to have an electric field. All electrons have an electric field, and if it's not moving, that's the only field that it has. But if we look over here and it's talking about a moving electron, well, now if we understand that moving electrons also have magnetic properties, then our moving electrons are also going to have magnetic fields. Sounds pretty simple. It's just a matter of understanding when to pick magnetic or not. So electrons only have a magnetic field if they are moving. Electrons will always have an electric field. All right. The last little bit of information that I want to give you today, talking about electromagnets. So I used this word earlier, and now I'm going to give you a couple of examples, okay? So again, we're merging the word electro, which actually is a word all by itself, but it's used for thinking of an electron. Maybe you think of an electricity or an electric current. That's the thought that I need you to have right now with this electro part of the word. And then obviously a magnet is a magnet. So there's two ways that we can create what's called an electromagnet, which is going to have both electric and magnetic properties. The first way is for us to use an electric current in order to create a magnet. So we're going to use electricity, moving electrons. An electric current is just a phrase that means that we have moving electrons. Now, if you understood the conversation on this slide, then you already know moving electrons are going to create magnetic fields. So this is why it says that we're going to use the electric current, which means moving electrons. That's a vocabulary word for the next chapter. So if we have moving electrons, then we're going to be able to create a magnet. And so here's an illustration of how that works. I have a battery which has a positive and a negative end. Again, we'll talk about that in a later chapter. But what this does is it allows my electrons to have a reason to move through the wire. Now, in this illustration, you can see that the wire has been wrapped around a piece of iron. Now, there are only certain materials that are magnetic. Iron is one of them, and so this example often involves wrapping a wire, or what we call a coil, around an iron nail because iron is magnetic. So when this wire is wrapped around the iron, when the circuit is complete and that wire is attached to both ends of the battery, that causes the electrons to move. Once these electrons begin moving, moving electrons also have magnetic properties. So as these electrons are moving through the wire, they are going to then induce, which is just a fancy word for create, a magnetic field. And so now the electrons on that iron are going to be influenced by the moving electrons from the wire, and they are going to pull those iron electrons into the same rhythm, into their same pattern, until eventually all of those electrons are aligned and we get a magnetized nail. And so what it's showing you in this illustration is that this nail has become magnetized and is now able to pick up these paper clips. So that's option number one. Option number two is going to be in the reverse nature. We're going to now use a magnet in order to create an electric current. So now we are going to use a magnetic field in order to cause the electrons to begin moving, which is going to create electricity. So in this illustration, what we are seeing is a magnet that is being moved inside of a coil in order to cause a light bulb to turn on. We're creating that electric current or electricity to power our light bulb. So here is my wire, or here is my coil, and let me change that color. And so this coil right here is basically creating a tunnel, and they are taking this magnet and they are simply moving the magnet forward, move the magnet backwards, forward, backwards, and they are just going to move this magnet back and forth repeatedly and very quickly. Every time that magnet moves through the coils, the electrons that are inside of the wire are going to be affected by that moving electron. And those electrons are in the wire are going to follow the magnetic pull from that moving magnet. And so as those electrons follow, they move. That is an electric current. That creates electricity. And voila, the light bulb turns on. That's what it's trying to show you in this illustration. So these are your two options. You will need to be familiar with what are the two ways that we can create an electromagnet. So let's just review them. One is to use an electric current in order to create a magnet. That is option one. What do we want to do in order to make my magnet stronger? Let's say that my nail is magnetized, but it's just not a strong enough magnet in order to pick up all of the paper clips, or maybe I have some heavier object than the paper clips and I just need a stronger magnet to accomplish that. Well, it's saying here there are a couple of things that you can do in order to make your electromagnet stronger. You can simply wrap that wire around more times, give it more coils around that iron, or you can just use a stronger battery, okay? Option number two is where we're taking an electric current and we're using that in order to create a magnet. And so now, oh, I said that backwards. We're using a magnet in order to create an electric current. So again, we are moving the magnet through the coil in order to create electricity. And if that is not strong enough, what can we do in order to create more voltage, in order to create more electric current? We can also put more coils, just simply make that tunnel of wires include more wire. And so that's just going to give you more electrons to move, increasing that electric current. Or you can use a stronger magnet, because the magnet is what is driving the movement of the electrons in the first place. So these are your two ways to create an electromagnet. So you're going to need to know all magnets have a north and south pole. North and south poles cannot be separated. Electric charges can. We need to understand the electric field lines go out of the north and into the south, and we need to understand the difference between moving electrons in order to create a magnetic field and stationary electrons that do not create a magnetic field.